It's after the Carboniferous. We just saw large trees grow out of the ground. We just saw large fungi grow out of the ground. What more could we possibly want? It was a period of stable terrestrial growth in plants and animals. There was the large growth, the large increase, the large biodiversification of insects, such as large dragonflies, and then there was also the development of amphibians onto land. But, although peaceful, something lurks towards the end. So, today we're talking about the Permian. I don't think the Permian gets a lot of credit. Um, that's my main point of this entire thing. So, welcome back. 2 week break. I'm pretty sure it was 2 weeks unless I'm really unorganized. But welcome back. Today, yeah, Permian, as I said. So, the Permian is really important. Like, it was the first period before the dinosaurs, and that's a pretty dramatic shift. So, first things first, we're going to talk about animals, which is honestly going to be a very small section because there isn't much of a difference from the Carboniferous. And then we're going to talk about the mass extinction event. It was pretty big, pretty drastic, pretty life-changing. I mean, it's a mass extinction event, obviously life-changing. So, let's dive right into it. So, at the time of the early Permian, animals were distributed amongst fish, amphibians, and reptiles. And from the journal that I looked at, they looked at a particular place of the Permian. It's currently north central Texas. So if you want, take out your cowboy boots and hats. I don't know what they look like I don't know what they were in Texas. So, anyways, at the time, in that Texan region, there was a delta, with the sea bordering to the south and west, and the land bordering to the north and east. The temperature was moderate. It was okay. I mean, it had to be, otherwise animals and plants would not have survived. So, rainfall was adequate enough for plants to live, and there was enough rainfall to supply water to fish and amphibians that live in ponds, lakes, rivers. It was enough rainfall, you know? Yeah, that's about it. And then, I think, yeah, overall, during the early Permian, there were 4 habitat subzones, which had vertebrates living in them. So there were ponds, which is like a wider group, which includes streams, ponds, and lakes. That's a bit misleading, but that's how the journal said it, so we are going on with that. Pond margins, floodplains, and divides. And for simplicity reasons, we're gonna call them uplands because I personally don't know what divides are. So, yeah. So these subzones should not be considered different habitats. They should not be thought as separate, but they should be thought as the principle. And they did not change habitats, feeding habits, behavior of animals. So it was just different areas where different animals lived. That's the basis of them. And these subzones can be characterized by different physical characteristics. So, for example, sediment deposits and the height of beds, embankments, I think they're trying to say. Yeah. And it can also be characterized by internal characteristics, such as a size and arrangement of soil grains by comparison. A lot of geology here, yeah. But then you might be like, oh, what animals? I want to get into the animals. I don't want the geology. What is this? I'm getting into that. Sorry. So, yeah, obviously, since the Devonian or Silurian? Silurian? No, Devonian. there's been a lot of fish, because that was a fish biodiversification event. A lot of fish came out of the Devonian. So many of the waters were inhabited by small fish, also known as paleoniscoids. Paleoniscoids. Nailed that. For the most part, and they became like a stable, important part of the food web. So they're really, really important. Yeah. Reptiles were also pretty new to the ring. They were new. They were pretty primitive. One early species includes Simoriamorpha. There we go. Simoriamorpha diadectomorpha. Simoriamorpha diadectomorpha. Absolutely nailed that. Anyways. But yeah, there were also Dimetrodons sounds better. So one way I can kind of characterize them is if you take a 4x4 truck, replace its legs with tiny stubby legs that go off to the sides, give it kind of a crocodile face, but smush that snout a bit inwards, like make that snout a bit shorter, and give it a sail, like a Spinosaurus, and a long tail, that's a Dimetrodon. They are usually thought to be like the first ancestors of dinosaurs. I must say, that is majorly untrue. Yeah, that is majorly untrue. So, you might want to change that. But anyways, we are going to go into dinosaurs next episode. Since after this is the Triassic. Yeah. Anyways. Remember when I said something about, like, the subzones? Pond margins. Remember the pond margins? They are, were largely restricted to the delta. So, for example, in north central Texas, that area, they had the Eriops megacephalus, which I think is an amphibian. Yeah, it was an early amphibian. And then the ponds and lakes were also known to not exceed the limits of the delta. The delta just kind of kept everything in there. So now, remember a couple episodes ago, I think I said something about sharks. Yeah, no, carboniferous. I think I said something about sharks. Anyways, one significant one was Xenacanthus, a prehistoric shark. And honestly, they were small, pretty cute, and they had a weird sharp rod coming out of its head, pointing backwards. It looks like a radio, what are they called? The radio sticks. I don't know like the ones that come out of cars. I don't know what they call them, I'm sorry. There were also lungfish, specifically Nachthorzia. They also appeared. So yeah, lungfish, most of them are dead, but in this day and age, today, most of them are extinct. But some of them are still here. Sharks, obviously, still here. Yeah. And I also talked about streams, a couple minutes ago. So there was no doubt the streams were fed by higher streams at higher altitudes. But, there was no evidence that there was significant migration from, the deltaic and non-deltaic streams. So a lot of the organisms just stayed where they were originated. I don't know where they remained, I guess. About the well, as I said before, the small fish were everywhere. The paleoniscoids were everywhere. Yeah, that's shown. And they were also shown to be part of the food web because coprolites, fossilized poo, of Xenacanthus indicate that paleoniscoids were sources of food due to the presence of scales. So, yeah. And that's how most organisms are found to be, prey or predators of other organisms. Anyways, but as I said before, zoology of the Permian period is not the main reason why we're here. The main reason why we're here is the end Permian mass extinction. It was so significant that it literally highlighted the difference between the Paleozoic and Mesozoic times. Like, Paleozoic is from the end of the Permian to, what was the first one? The cryogenic. That is a long period of time. The Mesozoic was the dinosaurs, and a bit longer, I'm pretty sure. Yeah, it was. Anyways, it was such a big mass extinction that paleontologists just used it to highlight a difference between times. A lot of the species went missing, but then they reappeared in the middle Triassic. So there's like a 10 million year time period where these species literally did not exist. That's kind of shady. Where are you going off to? Where are you leaving to? That's a bit weird. Anyways, also, many families went under major change, so, like, they adapted a lot, and so they were assigned to new families, even though there was no change in the lineage or extinction to the lineage. It's a bit weird. Personally, why wouldn't you classify it under the same family and just write, oh, there was this and this change, but paleontologists do what they do. Anyways, there are, so I'm going to cover marine, terrestrial fauna, and terrestrial flora extinction. There's quite a lot. So, if you're listening and you're still here, and if you want to learn about me ramble on about the Permian extinction, just sit back and relax. You're going to be here a while. Anyways, okay. So, marine extinction began at the end of the Guadalupian. So, it was like the second to last period within the Permian. Yeah. And it extended until the early Triassic for 5 to 8 million years. That's pretty long. So, here's the statistics for you. Global marine diversity declined by 54%. And generic diversity declined from, now these data are a bit weird. So I think, because I took this from the journal, I think they're trying to say the percentage of declination went from 78% to 84% in the last two stages of the Permian. It's not that clear, but I think that's what they're trying to say. Anyways, but then, at the time of this journal being written, refraction analysis showed that species diversity may have dropped by 96%, actually. So, 4% of species left. That's a lot. Life as we knew it could have possibly died back then. So, man, are we lucky. Okay. Those who were particularly hit by this in the marine ecosystems were the epifaunal, yeah. They were sessile filter feeding groups, and they had dominated the Paleozoic. They were like the big guns in the marine ecosystems, but they got extinction. No, I can't phrase it right. Yeah, they got, blasted away. Sorry. Building up on that, 98% of crinoid families became extinct. 96% of remaining tabulate and rugose, no, there's no R in there. Rugose corals became extinct. 78% of various brachiopods, remember brachiopods are like clams, but they're really rare these days. Anyways, 78% of various brachiopod families went extinct. 76% of bryozoan families, 71% of cephalopods. Cephalopods are like today's soft-bodied, like octopi, squid, cuttlefish, that family. I love that family. They're cool. Anyways, and 50% of foraminifera families. So, mass extinction. A lot of destruction, mass extinction. But you know who got lucky? The sponges, the gastropods, and bivalves. They got lucky. But then, like, at the time of this journal being written, modern evolutionary fauna only declined by 27%. So it's the studies don't really correlate. One study says this and the other says that. So I'm not sure which to trust, but please hold and let me continue on with telling you about the mass extinction of the Permian. Anyways, now backtracking a bit, I'm gonna detail what happened. Well, not what happened, like what happened to those families during the Permian. So, for example, the tabulate and rugose corals were in decline during the Permian. They were, I'm afraid, going to be extinct anyways. The bryozoans had a gradual decline during the Guadalupian and the Zolfian. Guadalupian and the Zolfian were like late stages in the Permian. So, with a 76% familial extinction and 86% gradual extinction. So, quite a lot of them died. And then there was the foraminifera, which showed a progressive decline, and then a rapid decline at the Permian-Triassic boundary. And then the fusulinids were like the dominant beneathic forms of the Permian, so they lived at like the low water columns during the Permian, but then they were eventually wiped out. So very, very sad. Anyways, now we're on to the extinction of terrestrial fauna. So, early work on the extinction rates of terrestrial tetrapods show that upper Permian extinction rates did not correlate with the marine extinctions. But at the time that this journal was being written, there was more detailed research that indicated extinction at the Sacmarian and Artinsican. These are periods of the Permian. The Sacmarian and Artinsican was pretty early, I think. It was pretty early. There was 58% of families went extinct. And then the Zolfian Scythian, that's a bit later, 49% went extinct. And then there was a Carnian and Norian, which were the late Triassic, part of the late Triassic, and 22% of families went extinct. So, yeah, quite drastic, quite a lot went extinct. Now, continuing on. So these extinctions were marked by the replacement of the labyrinthodont amphibians, anapsids, and the replacement of the early therapsids by the early diapsids. And there was also the replacement of the new families of therapsids. So, quite a lot of replacement of the amphibians and reptilians. Pretty sad. Anyways, the And then the new research, the more detailed research, not the early research, showed that peak extinction rate occurred in the Disolphian, which coincides with the peak marine extinction rate. So everything is very, very hypocritical. Everything points to one thing, and the other doesn't point to the other. I don't know which is which. Now, talking about extinction of terrestrial flora. So, climate's dried out. Why? The end of Permian Carboniferous glaciation. Yeah, so a lot of conifers spread to lowlands, replacing pteridosperms and pteridophytes. Yeah, just competition, out-competing, adapting better than the pteridosperms and pteridophytes. That's the circle of life. By who? Charles Darwin. Yeah. Anyways, in Gondwanaland, I think I talked about this before. Yeah. The deciduous and cold-adapted pteridosperms were unable to migrate as the climate warmed, and the northern pteridosperms moved south, which eventually, established the Triassic Gondwanan flora. Anyways, the Permian and early Triassic had a mixture of Palaeophytic, so plants before the Mesozoic, and Mesophytic plants, so plants from the Triassic onwards. In different regions, they were, they lived in harmony until the Mesozoic plants went, no, I'm going to fully establish myself, and, conquered the land. Anyways, the new mesophytic plants included conifers, ginkgos, cycads, cycadioids, and a new mesic group of pteridophytes and pteridosperms. So, all in all, not a very significant revitalization of plants, but, it was pretty significant that the Paleozoic plants of, the past couple of hundreds of millions of years got outcompeted by these guys. Anyways. So the pattern of change of plants is consistent in an increase of global aridity, global dryness, and continental seasonality. So, driven by climate change, a lot of stuff. And the 50% of diversity of plant families during the Permian and Triassic was spread over, the decline? I think that says the 50% decline in diversity of plant families during the Permian and Triassic was spread over 25 million years. So, it's gradual. So, if I were living at that time, I would not think, ooh, significant change. That would not be a significant change. That is a very, very gradual change. Anyways. What? Yes. There was no evidence of, a drastic extinction at the end of the Permian for plants. There was a drastic extinction for animals, but just not for plants. There was no evidence for a drastic extinction of flora at the end of the Permian. Gotta establish myself. Rather, an extinction of flora. Well, I just said it was an extinction. A reduction of flora was due to the ability of different families to migrate and adapt to new environmental conditions. So, if you couldn't adapt, practically you're dead. This is evident because plants are generally immune to mass extinctions because they've got root systems, sperms, and rhizomes, seeds, but plants are also very vulnerable to competitive displacement and climate change. So once someone gets in their personal space and they get less sunlight, they will die, literally. They are they care about their environment. Anyways, there was a lot of change during the Permian. It was more of a transition instead of a period, I'd say. Yeah. Anyways, marine regression. The ocean literally shrunk back. So, the Permian was a period of continuous marine regression from the Saccarian to the Permian Triassic boundary. The ocean literally just retreated. Yeah. And another physical environment change is climate. So, I don't know if you know this, but like Pangea formed during the Permian. The Permian, Pangea. Yeah. I didn't know that before, researching this, and I was surprised. Anyways, the formation of Pangea definitely had a drastic effect on the climate. Pangea was like the supercontinent. It was a mass continent. And because a lot of land was landlocked, the center of the land was majorly dry and arid. It's got deserts and stuff. Anyways, following the end glaciation in the Saccarian, the climate became more warm and arid. Arid as in dry. And then sedimentological evidence indicates that mid-Permian climates were warm, but that wasn't like very equally distributed. And high seasonality was prevalent, and all this was caused by the formation of Pangea. So evidently Pangea caused a lot of problems, even though a lot of people go like, oh wow, it's so cool. And then in India, China, and Russia, coal deposits indicate a temperature latitude region of high humidity. I think on the map of Pangea, it shows that Russia, China, and India are on the seashore, the ocean side. They're coastal. So, it was humid on the side, and it was dry on the interior, in the continental interior. So, quite a big drastic change. Anyways, so Pangea actually rotated, tectonic activity. Tectonic plates move, obviously. But Pangea rotated, causing Siberia to be near the North Pole, and Australia and Antarctica to remain near the South Pole. And so the proximity of the land near the poles steepened temperature latitudinal gradients and led to a global cooling effect. So the Permian's like a period of fluctuations in global temperature. This period was crazy. This period went from being stable to absolutely, I forgot the word. What is the word? Apocalyptic, kind of. Yeah, that is the word I was trying to look for. Anyways, there were, again, glaciation occurred again towards the end. There was a Permian Triassic glaciation, which may have been caused by the cooling effects of volcanic activity towards the end of the Permian. So everything was crazy. Everything was crazy in this time. Everything was crazy in that day and age. And then there were ocean fluctuations in the middle and upper Permian with a 2.5 million year cycle, which indicates glacial pulses. So water is being formed as glaciers, but then it was melting at a higher rate, but then more glacier was being formed, and then more was being melted. It was crazy, but this does not correlate with the Milankovitch cycles. So, to fill you up on the Milankovitch cycles, if you don't know what they are, it's like when the Earth's orbit or tilt on an axis changes, and It's like a 1,000-year cycle. It's a couple 1,000-year cycle. No need to worry. Obviously. So it changes the distance of the Earth from the sun, and depending on the tilt, or depending on the distance from the sun, obviously, it changes seasonality, it changes climates. Sometimes it causes increased global global warming. It's quite a lot. Anyways, yeah, as I said before, interior areas of Pangaea suffered from higher seasonal changes due to the lack of ocean affecting local climate. The ocean's really important. Like, take the UK for example. How close are we to the Atlantic Ocean? How close are we to the British Channel? Pretty close. We're an island, obviously. And the Gulf Stream is like ocean current that starts in the Gulf of Mexico and just goes up and it sinks near the North Pole and comes around and back down, and it causes like a cooling effect. That's a rough summary for you. Anyways, the formation of Pangaea was crazy. It caused a lot of problems. It produced extreme fluctuations in seasonality and the formation of severe monsoons in continental interiors in both hemispheres. Continental interiors, that's kind of crazy. The formation of tropical storms in continental interiors. They don't form on land. So the climate was so crazy that storms formed on land. Tropical storms formed on land. Hurricanes formed on land. Typhoons formed on land. No thank you. Anyways, two-dimensional energy models of the late and early Permian climate indicate high seasonality. Fluctuations in season, season. And listen here, listen carefully, listen properly. The average maximum summer temperatures were at 38 degrees Celsius. No thank you. Not only that, but possible daytime temperatures at 45 degrees Celsius. I am gobsmacked. I fear for the organisms at that time. And there was a 50-degree range in temperatures. What? Crazy. Anyways, but then these temperatures were also consistent with the evidence of glaciation in eastern Australia and Siberia, and also the distribution of terrestrial vertebrates. But it is important to note that like a vast majority of Pangaea was a desert, so it would have been really hot. The sand reflects a lot of the radiation. It also absorbs a lot of the radiation, so if you walk over hot sand, it's hot on your feet and hot air rising up into your face, obviously. So it would have been horrible. Other than, marine regression and shifts in stable isotopes. Wait, no. In climate, and there were also shifts in stable isotopes. I'm going to get into that. So there were shifts in the carbon isotopes, which demonstrates shifts in the burial of organic carbon, which seems to reflect changes in global biomass. Carbon isotope measurements in the brachiopod shells in Spitsbergen. I think is a place in Austria or Switzerland. I'm not sure. But it is somewhere with snow. Yeah. Indicates a period of increased carbon burial during the Upper Permian, followed by a period of increased oxidation of organic carbon. Chemistry! Yay! A core from the Austrian Alps indicates that the extinction event was followed by a several million year period of carbon oxidation, organic carbon oxidation. So, tons of changes, minuscule to major. Yeah. There was also shifts in carbon-13 isotopes from a negative shift in the Triassic. Wait, hold on. There was a slight positive shift of carbon-13 and then a negative shift in the Triassic, which can be associated to anoxic events. So when there's no oxygen, practically. No oxygen for respiration, no oxygen to survive. And it's crazy. This time period is crazy. There was, yeah, hold on. There is a explanation that marine regression allowed for the oxidation of previously buried organic matter to be exposed to oxygen. So this subsequently led to a decline in nutrient supply, which affected the marine primary supply, so the marine ecosystem, causing a drop in biomass. Links, feedback loops, crazy. And there was also maybe the oxidation may have reduced oceanic nutrients and atmospheric oxygen levels. So the extinction could be correlated with atmospheric oxygen depletion. This time period is crazy. Whoa, my eyes. Sorry. Sedimentological, evidence and simulation studies suggest that the increased burial of organic matter during the Carboniferous and Permian rates were followed by reduced rates as the Permian became more arid. Everything indicates, the climate changes everything. That's my point. It's crazy. Oh, other than carbon, obviously I've been talking about carbon for the past few minutes. There were also isotopic changes in the abundance of oxygen and sulfur isotopes. So together they show a dramatic change in water chemistry, but they can't explain the mechanisms behind extinction. So there was a change, but they aren't significant, or they can't be linked to it. There were also geophysical events. So a study of clay in South China showed that, were consistent with a silica-rich magma. The thickness and distribution of the clay indicates a large eruption of over 1,000 kilometers cubed of silicic magma. So practically it was a volcanic eruption that was humongous. These clays were likely to have been produced by subduction of oceanic plates. So a destructive boundary, you've got the continental plate, it's denser. It's denser? Yeah, I think it's denser. It's denser, it's thicker, it's older. Oceanic plate's newer, it's less dense. So when they move together, the oceanic plates, and they converge, the oceanic plate goes oh, no, I'm softer, I'm less dense, I'm younger as well. It sinks, and that's called subduction. And then the sunken part of the plate is heated up, and that creates new magma, and that causes the land to bulge, forming a volcano. And then if there's more friction when the plate subducts more, that causes an eruption. That's a general description. Anyways, so large volcanic eruptions would inject large amounts of particulates and gases into the atmosphere, and so this will create a mass cooling event, which may have led to the glaciation of land during the late Permian. And now we are going on to the reasons of extinction. There's so many reasons. This is practically 2 pages. Anyways, extraterrestrial mechanisms. So there were high concentrations of platinum group metals that were found. So, for example, there were suggestions that cosmic radiation may have caused an extinction event. And then further on that point, I'm gonna name some scientists. Hatfield and Camp suggested that the movement of the solar system relative to the galactic plane increased the magnetic field. Personally, I don't think that's correct, but I will continue on. If the movement of the solar system is perpendicular to the galactic field, it would increase magnetic field and cosmic radiation, and hence would lead to more mutations and extinction on Earth. So, I find that hard to believe, but I will continue because we accept all points of views. So, since mutation is linked to the intensity and duration of radiation exposure, the solar system would have had to stay on over the galactic plane over a long period of time. But now we're getting into the criticisms. The position of the solar system relative to the position of the galactic system is not known with certainty, but it does agree with the general timing of the extinction. So maybe it caused it, maybe it didn't. We don't know. And additionally, cosmic radiation is more quickly absorbed by water, so the greatest rates of extinction should have been seen in in marine ecosystems. Which, hold on, I think I take back my statement. I think this could be plausible. Not the most plausible, but plausible. It kind of works out. Anyways, environmental changes in salinity. So, there's research that shows that extensive Permian evaporite deposits could have created an extinction due to the brackish oceans that it creates. So, but there was a comparison of biodiversity from the late Permian, when they thought the deposits would affect stuff, to the Miocene-Messinian salinity crisis, and it was concluded that the salinity change in the Permian would be insufficient to cause mass extinction to fauna. So, it isn't the biggest thing. I mean, obviously, changes in salinity, it would affect ocean currents, it would affect the climates of areas, but no, it would not have affected anything. Additionally, building on that point, large deposition of evaporites occurred in the Hungarian and Middle Triassic, and there was no mass extinction. Weak argument, I must say. Weak argument. Global cooling. A lot of the world's mass extinctions occur in, drastic climate change and marine regressions. So, there is mass evidence that points to a fact of an increase in aridity during the late Permian, and there were higher temperatures, but this was interrupted by the glaciation towards the end of the Permian. This cooling period of the world may have caused extinction and affected land of the tropics. It could have, caused extinction of tropical species and specific temperature species. So, a lot was happening back then. A lot. Evidence of climate deterioration and global cooling incidents include progressive restriction of stenothermal taxa of low latitudes, followed by higher extinction rates and reduced carbonate deposition into the early Triassic. Crazy times. Yeah. And then there were also changes in the primary productivity, so changes in the food web. Terrestrial nutrients are vital to marine productivity. Now I'm gonna name drop the scientists right here. Tappan argued that the development of terrestrial ecosystems sequestered more nutrients that deprived marine ecosystems of nutrients. So sequestration is like the capture of a certain substance and storing it. So, for example, in terms of the carbon cycle, a natural sequestration event is trees taking in carbon dioxide for photosynthesis. And then it stores it. Well, no, it won't store it because it's used for glucose. But it is a physical sequestration tactic. Anyways, that the deprivation of the marine ecosystem of nutrients would cut marine primary productivity and cause mass extinction. But this would happen like over a long period of time. And marine productivity recorded in the shift of isotopes would have occurred far more rapidly than Tappan suggests. So it isn't the most valid argument. Additionally, Carboniferous terrestrial biomass changes exceeded those caused by a shift from Palaeophytic to Mesophytic flora, which took a longer time than an extinction event. So, the drop in marine productivity does not seem to be linked to long-term changes in terrestrial biomass. There isn't much of a correlation. And then my final, point of why the mass extinction event happened is tectonic activity. The formation of Pangaea was a disaster. It was a big problem. It created so many geophysical changes, which can be linked to the mass extinction event. So, for example, including the availability of shelf area for marine species. So, there's less habitats. There's, less shallow area. So this would have reduced biotic provinciality, and increased climatic instability because of marine regressions. The reduction of shelf area could induce a marine extinction if there's a linear correlation between species diversity and habitable areas established, which, there kind of is, but it's not always linear. But as I said before, just now actually, it's impossible to plot species area curves because, everything changes. You can't be that sure of something. You can't be like, oh, as there is this much space, there will be this many animals. That's practically impossible to do. There's so many other factors. And it's especially hard for marine organisms, especially back in that time. We don't know how deep the oceans went. We don't know a lot of things. So, yeah. And that, my friends, is the end of this podcast. That was a lot. I hope you didn't fall asleep. I hope you absorbed the information. But yeah, thank you for stopping by, and I'll see you guys next week.